Without translation, I would be limited to the borders of my own country. So said the Italian writer Italo Calvino. We all gain from being connected, being one mass also. And in this, the boundary crossing the role of the translator is obvious. Mathematics is the big translator of nature and the man-made world. Physics is all mathematics, for instance. Within the larger mathematics, it is function that helps us cross the boundary of our knowledge and the nature. Function is the most ubiquitous translator of nature into a language we know, mathematics. Adequate foundation of functions is presented in the lessons on trigonometry. We would do better by sticking to what is additionally meaningful about functions in studying calculus. Broadly, two aspects of functions need specific pegging. For a reaction involving reactants A and B, it is expressed as: first is discovering how many unique functions we need to know so that we can mathematize the behavior of most of the natural world, as well as technology and engineering. And how complex are these functions? Second, how do we get to develop functions that behave like the real world? The unraveling of the secret of diversity of functions is one of the most humbling and wonderful feeling one can live professionally. There are just a handful of functions that are deployed to mathematically represent the big part of the unfathomable expanse of the ever-changing and evolving nature. Of course, these small set of functions are mathematically combined to create infinite expressions of functions to match the infinite faces and behavior of nature, technology, engineering, and research. And there is more. Almost all of the functions in that small set are well introduced by the grade 10th. Naturally, what level of complexity and mathematical expressions can be expected by grade 10th? Little. We will explore 6 of those primary functions, enough to settle all anxieties about the notions of complexity around functions. Second, how do we come to evolve exact mathematical expressions, called functions, that most closely represent our world? How mathematical expressions come so real? What is in their conception and mathematics that makes functions so real? Functions are perhaps the best testament to the critical and creative expanse of mathematics as a language. We will get to this in the next lesson, and be ready to be unsurprised by the simplicity of it all. How real can only be understood and simulated by being real. Mathematics as a language is much like natural languages. We can express what we see, do, feel, know about anything around us. Except, of course, that mathematics expresses only the quantifiable world. Function is the most common and comprehensive form of mathematics as a language. In fact, functions are the default means of expressing the behavior of real-life situations and objects. We also directly use data for expressing reality, but even that indirectly uses functions. Whatever reality is functionalized is accessible, readable, and usable by all. Mathematics is the only universal language of people, machines, and the universe. And function is that part of mathematics that makes the real world accessible to us in a truly abstract way, to offer endless more insights and inventions. Now, just 5 reminders on functions. First, equation is the most common mode of expressing functions. This is only to remind why functions are simple and familiar to us. Second, a set of data, like matrices, may also indirectly represent functions. But the default is the direct use of functions, because in function form, we can undertake extensive analysis. Third, operations on functions lead to another function. Thus, the slope of a function is also a function. This is a very important feature of functions. For example, when we derive speed from distance-time function, we do not get one specific speed, we get a function for speed that gives us varying speed over time. Fourth, functions work on a set of data, called domain, and output a set of data, called range. The domain and range are sets, not individual data. This is what makes functions dynamic, be real-like. Mostly the domain of functions is the set of real numbers, and that means all possible values can be taken as inputs and processed for output. Fifth, functions in calculus are just as algebraic and trigonometric as it is, nothing special. This aspect of the use of functions in calculus may sound simple, but it is hardly internalized. What it implies is that the computations involved in calculus are nothing beyond the usual algebra and trigonometry. We have an illustrated lesson on it later, the last lesson on calculus. Slope needs a special reminder, being the spring of calculus. Rate of change is at the heart of differentiation, integration, and differential equations. The concept of slope can be traced back to ancient Greek mathematics in the properties of lines. The new thing about slope was that calculus rediscovered the idea of limit, and that was a sound way of finding the slope of curved lines. The slope of curved lines was a big deal because it held the key to find the slope of all kinds of shapes. By the way, the core of limit could be traced to the Greeks' method of exhaustion. The picture shows how Archimedes used the method of exhaustion to compute the area inside a circle. Slope as the rate of change of functions redefined our ability to capture the essence of change, and also to be able to quantify the relationship among changing quantities. Now, onto the first of the 6 of the foundational functions. It is the linear function. And do not take it lightly as being very simple. The graph shows a typical linear function. All linear functions of the type fx is equal to ax plus b can be derived from this parent function. A lot of things follow linear relationship with other things. For example, image processing in artificial intelligence often involves handling vast linear relationships through the use of matrices and linear algebra. A word on linear algebra would firmly place in perspective the importance of linear relationships. Linear algebra helps efficiently solve systems of equations. For example, for many equations with many variables, we represent them as matrices and then use much simple matrix or linear operations. This is the quadratic parent function. It is parabolic visually. All the quadratic functions of the type fx equal to ax squared plus bx plus c can be derived from this parent function. This is the parent function for reciprocal functions, such as 1 by x, 1 by 2x, minus 3, 5 by 2x. The graph of this function sees a vertical asymptote at x equal to 0. This is the parent function for square root. Functions of the type fx is equal to root ax plus b are derived from this parent function. The most common exponential function is ex courge, where e is an irrational number with value 2.718, just like the irrational number pi. It is a very common parent function, and functions like e to the power 1 by x, e to the power sine x, etc. are derived from this parent function. This is one of the trigonometric parent function. Other two are the cosine and tan functions. It is the parent function for functions such as sine 3 by 4 radian, sine 4x, etc. What is the one running thread through the 6 functions? To me, it is that functions are as mundane as these. To be sure, there is a small group of 11 functions that may be called the parent functions for innumerable more functions that could be created out of the 11. These are introduced in a separate lesson. What is most pertinent here is the stark fact that infinite realities need infinite functions, clearly a very disheartening demand. However, parent functions diffuse that demand, and we can create infinite functions out of just a few. I cannot even think of a fractional possibility of a small set of parents' functions being the fountainhead of most others. I wonder, this is humbling providence or heady human genius. Functions are really accessible mathematics, and they are very unfairly stigmatized as difficult and too abstract. It is easy to fall in love with functions, and you partner calculus along the way. We will discover next as to how the DNA of function is real bits, actual physical trace of the world. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.